mentors along the way. And, I tell folks about when I showed up at NASA and I'm full of piss and vinegar and I think I know everything. And there's all these veterans from Apollo that are around. And one of my first technical presentations, they just ripped my heart out. They just cut me up. And then not long after that, I was coming up on one of them in the hallway, and I'm like, oh no, and I'm sort of all meek, and he comes up, stops me, talks to me, says, hey, have you made any progress on this and that? But it was clear that he didn't think poorly of me. This was just part of, helping me grow. Okay. And, that Apollo culture was just fantastic. And I hope I captured a part of that in who I am, which is you don't run away from the hard problems. You run to the hard problems.
The following is a conversation with Dale Thomas. Dale is a NASA veteran of several decades and currently is a professor at the University of Alabama in Huntsville. Dale gave us the rundown on nuclear thermal propulsion and how it will be used in the next generation of space travel, along with what his role in that has been and will be. Dale also mentioned that he is working on his first scientific mission ever with a CubeSat that is entirely student-designed and built. However, that group is still awaiting funding from NASA, and they could use your help in the meantime. If you think you could be that help, there's a link in the description where you can find out. With that said, I'm your co-host, Douglas Schoenholtz. Your other co-host is Michael Hladky, and you are listening to Sci-Fi to Reality. Let's learn about nuclear thermal propulsion. Professor Dale Thomas, thank you so much for joining us today on Sci-Fi to Reality.
It's my pleasure.
So let's start off with defining what it is that we're talking about today. Could you tell us a little bit about what a nuclear thermal rocket actually is? And how that actually works?
Yeah, glad to. So a nuclear thermal rocket is actually a simpler concept than a chemical rocket engine. So and I'll start off with a chemical rocket engine because that's what everything is today. From the SpaceX Merlin, go back to the Saturn V, everything is chemical rocket engines. And in those, you mix a fuel with an oxidizer, okay? And much like in your engine in your automobile, you get combustion. That combustion releases a lot of energy, creates a lot of heat. That heat, is included in the exhaust gas. In the rocket nozzle, you're directing that exhaust gas, that very hot, high velocity gas, in the desired direction. And just by conservation of momentum, when you have that stream of hot gas going one way to high velocity, it imparts an impulse to whatever else is out there in the other direction, which is in general, the rocket. Okay. Well, just like in your automobile, combustion is not easy to do right. It is fairly complicated, and that's why, rocket engines are hard to build and hard to build well. Okay. Now, with a nuclear thermal rocket engine, you're creating that heat and introducing that energy via a nuclear reactor. Okay, not unlike what they do at the nuclear power plant down the road. I'm not sure what the closest one is to where y'all are sitting, but the nuclear reactor just sits there, and you're sharing neutrons. The neutrons cause uranium-235 to split. Energy is released, and more neutrons, and you generate a chain reaction. But the thing is, it's sitting there generating heat. Now, if you generate too much, you get a hot mess at best, and you may get an explosion at worst. Okay. So you want the heat, the neutrons being generated and the heat being released at a controlled rate. Okay. Just like you do at the nuclear power plant down the road. Well, what you're doing in the nuclear engine is, you have that reactor in there generating heat. Well, that's a very natural process. Okay. You don't have to manage all the complexities of combustion. You just have to manage the complexities of that nuclear reaction so that you're generating the heat at the right rate. And the propellant that you're running through is not combusting with anything. It's just removing the heat from that reactor. So it's getting its heat out by, if you will, cooling the reactor, much like the coolant in your automobile, it circulates through the engine to keep the engine from getting too hot. Okay. Well, in this case, that's what the propellant is doing in the nuclear thermal rocket. It's running through the reactor, removing heat, and in the process of getting, real hot, it's, you have all that energy in the propellant, you direct that out the nozzle, and you get your impulse that way. Now, the neat thing is, with chemical engines, you're reacting two elements, like kerosene and oxygen. And I say elements, two compounds, I should say, like kerosene and oxygen, or in the higher performing engines, like hydrogen and oxygen. And the reason hydrogen and oxygen is a higher performing engine is because hydrogen has a lower molecular weight. And when you're looking at the impulse, that force you're imparting, you will get more from a given mass of hydrogen than you do a given mass of kerosene. Okay, just simply because it's lighter, and so it accelerates faster out the nozzle, all of the things being equal. Okay, well, the neat thing is, with a nuclear thermal rocket, you can use hydrogen. You don't need to introduce another heavy element like oxygen, to release the energy. It just removes the energy straight from the reactor. So you get nominally twice the performance of the best chemical rocket, okay, out of a nuclear thermal rocket engine. So a common measure of efficiency is called specific impulse in a rocket engine, if you're familiar with that. Impulse is just the amount of time that you can create a force or an impulse equal to the mass of the propellant that you're using. So let's say you've got a pound of propellant. The amount of time you can create a pound of force with that propellant is called the specific impulse. Okay, so the best chemical engines, like the Space Shuttle main engine, will give you about 450 seconds of impulse. Very, very good. Okay. By comparison, the Merlin engine on the SpaceX rocket, that's an RP or a kerosene engine that's reacting with oxygen. Both of those are more heavy elements. It's down near 300 seconds of impulse. Okay, so lower performance. Okay, contrast that with what you get with hydrogen flowing through a nuclear reactor. You're getting up around 900 seconds of impulse. So you can see you're basically at about twice the performance of the best chemical reactions. And what that enables you to do, it just opens up where you can go. It's like having your car and all of a sudden you can go twice as far on a tank of gas.
Okay. For sure. So I want to get into all those nitty-gritty details in a minute, but taking a step back for a little bit, could you walk us through a little bit how you personally got into mixing two of the most complicated engineering fields, rocketry and nuclear engineering, and what your personal journey has been?
Well, I'd like to say it was all plotted and worked out and intentional, but the only thing that was plotted and intentional is when I was a kid, even younger than you. So I'll just say in the 60s, I was fascinated by the Apollo program. My dad was an engineering technician, worked with General Electric, and he actually built some of the ground support equipment for the Saturn V. And I was very fascinated by the whole moonshot program, and I wanted to grow up and work for NASA. And I was able to do that, be an engineer, got a job with NASA, and started out working. The International Space Station was the first program that I worked, in much detail. And then over my career, I worked other projects as well, including the Constellation program back in the 2007 to 2010 timeframe. And, then that morphed into the SLS and Orion program, which, are slated to launch later this year, more probably next year. But so my NASA career got me into rocketry, moving around. And then after I retired from NASA back in 2015 and joined the faculty at the University of Alabama, Huntsville, they had established the nuclear thermal propulsion program out at Marshall Space Flight Center, NASA had. And I was talking to some of my former colleagues in that office, and they were looking at some aspects of that and basically asked if we could put a research program together to help with that. And we did. And we're focused in nuclear thermal propulsion a little bit on the program that they're looking at to fly, but our primary focus is we're looking at the next generation of nuclear thermal propulsion. Okay, I'm going to get weird on you here, where we're actually wanting to get that even more heat into the propellant. Okay, so one of the constraints on the nuclear reactor at this point is how hot you can get it before you start melting all the parts, right? Sure. When it gets too hot, like I said, you have a hot mess at best case and an explosion worst case. Don't want that. So, that limits it. But boy, if you could uranium will get as hot as you'll let it get. Okay. And so could we let it get even hotter, let it liquefy into liquid metal uranium, and then get the heat transfer out of that, and that gets you that impulse, that measure of performance on up now in the neighborhood of 2,000 seconds. Just another game changer. Now you're talking about being able to launch a mission out of the Cape and fly to any planet in the solar system, even out to the Kuiper Belt, a scientific mission, okay, without having to wait for all the planets to line up so you can fly these sophisticated trajectories. You can say, I want to go to Pluto. Okay, I can design a mission to Pluto, and you have one opportunity at least every year. So it's just a game changer from exploration. Of course, there's these little things about how do you contain liquid uranium, because it wants to melt everything around it. Okay, so we're working on that. But you sort of asked, how did I, get into all these things? Well, we sort of have stumbled into them. The intentional step was getting to work for NASA, which was, a great ride. The only reason I retired from NASA was to get this research opportunity at the University of Alabama, Huntsville. And then about that time, this big technological challenge of nuclear thermal propulsion comes up. And so I've gotten involved in that. So it's been, a little bit of planning and a lot of serendipity is the way I'd answer your question. And I know that's a long, rambling answer, but it's not, I can't give you a simple story,
Sounds like things worked out for you. So just for context here, how long have you been working on the nuclear thermal rockets? When did that start being a topic of research, really?
Okay. How long have I been working on what?
The nuclear rockets.
Oh, I believe we started that. And when I say we, I say my own effort. Started in 2017. Okay. Now I know there are a few people at NASA who go well on back, to shortly after 2000. But it took a while to get advocacy inside the agency. For a long time, nuclear was a 4-letter word. Everybody was scared of it. Radiation, bad, all that kind of stuff. But finally, things fell into place that the agency opened up a little bit we could really do, some amazing things from an exploration standpoint if we had more efficient, more powerful engines. It's sort of a limiting factor on where you can go. Basically, with our current suite of chemical engines, we can get to Mars with a human mission. It's really hard to do, as you may have, if you've read some background. Things have to be just lined up just right. You really need nuclear thermal to get to Mars unless you have in situ. And if you look at, for example, what Elon Musk has been talking about, he flies to Mars with a chemical engine, but then he tanks up on Mars to fly back. So my point is, Mars is sort of at the edge of the envelope with regard to what you can do with chemical propulsion without doing the fancy planetary assist trajectories. If you're really wanting to explore, we got to have better engines, in a nutshell. And so that's sort of what it gets down to. And I don't know if I answered your question or not. I may have gotten a little off track. So feel free to ask me a follow-up on that.
No, you covered it. You're good.
Okay.
So I'm excited that you already mentioned that you guys are looking at liquid core NTP. Could you expand a little bit on how you guys are going about how you guys are going about liquefying the uranium and how you're going about containing that?
Well, so sure. So the concepts for we call it liquid fuel NTP because your uranium is really your fuel. While it's not technically burning, it is sitting there splitting and so forth. But anyway, several concepts were researched for this back in the 60s. So if you go back into the late 50s, the 60s, and the 70s, there was a program called NERVA. I don't know if you've run across that in any of your background, but they actually built. When I say they, it was a joint. I think it was joint NASA Air Force. I know NASA was active in it. But anyway, they actually built a nuclear thermal engine. Okay, tested it out in the Nevada desert and ran quite a bit of testing on that engine, and everything worked. And then in the early 70s, when NASA decided, no, we want to focus on shuttle and low Earth orbit, that program was shut down because even then, the physics hadn't changed. They knew we needed better engines to go further out into the solar system. But the good thing is there's a lot of engineering there that is providing the basis for what is being done on what I'll call the first generation nuclear thermal rocket engine today that's being worked, that they hope to be flying later this decade, okay? Or at least on a demonstration flight, I'll put it that way. Now, while that was going on, you do have engineers and scientists saying, okay, hey, we can do a lot more with this if we can get out of the constraints of, solids. Okay, so what can we do? So several concepts were developed. When we looked at the different concepts for doing that, it looked like the most viable, I won't bore you to death with all of them, is one where you let the uranium heat up. And like I said, if you're just sitting there bouncing enough neutrons off of it, it'll keep getting hotter and hotter until you slow that down. Okay. So getting the uranium to liquefy is fairly straightforward. Now, keeping it from melting everything around it, that's a little more complicated. The concept we have is we're going to have the uranium. We're going to put it in a cylinder that will spin, and it'll spin very fast. And so we'll use the centrifugal force, to keep the uranium glued to the walls. And of course, it'll be capped at the top, and it'll have a taper at the bottom. Okay. So ideally, that will contain the liquid uranium. And we're going to bubble hydrogen gas into it, although, you could do any gas, heavier gases like nitrogen or argon or different things. You just get lower performance because of the heavier molecular weight. Okay. But bubble and also hydrogen, since it's such a small molecule, it solves a problem I'm about to tell you. We're going to bubble it through a porous wall. So the wall will have teeny tiny holes in it that will let hydrogen through, but not let uranium out. And keep in mind, you're sitting there spinning that cylinder fast, so the uranium's going to be glued to the wall. But like I said, we're going to push hydrogen gas through the wall at high pressure. And as it bubbles through, it's going to cool the liquid uranium. You'll have heat exchange between that liquid uranium and the hydrogen gas or hydrogen propellant. And so you're getting that hydrogen propellant up around nominally about 5,000 degrees Kelvin. And so it's exiting that engine, at bat out of hell speeds. Okay. You're really getting high performance. And that's where the impulse comes from.
Sure.
Okay. So, yeah, some engineering problems to solve on that, how to make sure we keep all the uranium contained. What type of material can you come up with that will contain uranium even under good centrifugal acceleration, and yet it'll let gaseous hydrogen permeate? There's some engineering problems, and plus we don't really understand very well the thermodynamics of heat transfer between liquid metal and a light gas such as hydrogen. Okay, we've made some assumptions, first order assumptions, back of the envelope stuff, but where we've started is we're actually developing some theory and some laboratory apparatus to let us look at heat transfer between liquids and bubbles, if you will. We call it Bubbly thermodynamics. And if you'd have told me, 30 years ago when I was an engineering student that someday I would be creating bubbles in a laboratory, I would have laughed at you. Okay. But this is exactly what we're doing. And like I said, we're trying to understand the dynamics of the bubbles. Like, for example, we're assuming we have to get so much mass of the hydrogen through this engine and out, to make it balance thermally. Okay. Well, like I said, we want the hydrogen, we need those holes to be very small for the hydrogen to come through. Well, that implies you're going to get very tiny bubbles. Can we get enough hydrogen flow rate through those tiny holes? Okay. Or do we have to make the holes bigger? And if you make the holes bigger, is the uranium going to seep out? Yeah, there's a lot of engineering to be done here.
Yeah, for
and
sure.
That's what we're working on now, is trying to develop some basic theory on bubbly thermodynamics and correlate it with what we're doing in the laboratory. Can we validate our theory? And as we start understanding the basic engineering from a physics standpoint, it's fairly simple. Okay. Can we understand it? And that involves also some things like we're assuming given rates of heat generation. Fortunately, we have some colleagues at University of Penn State in particular and University of Michigan who are running the neutronics models to say, this is how you will, get the uranium to heat up. And once you have it at your target temperature, this is how you will keep it there. And then eventually how you will cool it down when you want to ramp the engine down. So we're trying to work the generation of heat, the transfer of heat to the propellant, and also the control of the whole mechanism.
So
in a nutshell.
On that last piece, could you explain how you do cool the reaction down in a safe manner coming from a naive perspective?
It's actually fairly straightforward. You'll actually set up on the reactor. You have reflectors on the outside that bounce neutrons back into the reactor, if you will. And it's set up such that, and this is part of the neutronics, is getting that in balance, so that when those reflectors are, if you will, when they're configured so that they're not bouncing neutrons back, you don't get enough neutron impacts in the reactor and it just starts shutting itself down. Okay. And then when the reactors are on full, it heats up fairly quickly, and then you can control it between those two settings. Okay.
For sure.
And that is part of the sophisticated engineering that, like I said, our colleagues at other universities are working on, because at UAH, we know rocket engines, but we're not nuclear engineers, so we're having to work with some colleagues on that.
Right.
So did that answer your question?
Yes, it did.
Okay.
Thanks a lot. That was something I've wondered a lot about, and I haven't just taken the time to read the Wikipedia article on. I think so. It's very cool to see the perspective on it.
So to clarify, the work you're doing right now, it's still very theoretical, kind of working out what kind of parameters you can use to potentially design the rocket itself. You don't have actual functioning rocket engines, or
so for in the context of the liquid fuel NTP, no, that's a ways off. We're not even ready to develop a prototype of that yet. We're still trying to understand the basic engineering principles at play. So we've got a ways to go on that yet. Now, the solid fuel NTP engine, that's what is currently, being developed by NASA, and we are supporting them in that one as well. And that's the one that, they are trying to, when I say trying, they are actively working with companies in the field like BWX Technologies, UltraSafe, and government organizations like Idaho National Labs, Oak Ridge, so, and they're building on the knowledge base of the NERVA program. And so, yeah, they're on a track. Their main challenge in that project, and I'll call that, like I said, the near term active project. What we're doing is with the centrifugal work, that's the follow on. Okay, the longer term work, assuming we can make it close, if you will. But anyway, the big challenge they're working on, the solid fuel, the current program, if you will, is manufacturing those fuel elements, okay, that will withstand the temperatures and pressures for the amount of time that those engines need to operate. Okay, because if you get a crack in one of those fuel elements, the hydrogen is going to start getting in there and reacting with the fuel, and it's just going to degrade things. So can you come up with the right materials, with the right parameters, the right coatings, such as this engine will not just work on the test stand for a few minutes, but will work for repeated burns, like your Earth departure burn, your Mars entry burn, then your Mars departure burn, and your Earth entry burn. You need to be able to power it up, shut it down, let it cold soak for months, and then power it up, shut it down again. So that's, those are the real challenges. Can we make this reactor, that will function in that manner, to support the missions that we're wanting to do with it.
Is there one part of the engineering process you say that's going to most heavily lean on that aspect, where you will have to really make sure you drill down and make sure it's tested for 6 months of viability and for a mission or something like that?
Yeah, so and that is essentially what they're driving now. They have something called a design reference model, and so they're backing out all the parameters that they will have to test to on the ground, on the individual fuel elements, to say, yeah, we think we have got the answer here. Our data correlates, and then ultimately, to get you what you're talking about, then they will do, demonstration flights. You're not going to put a human crew on the first engine, to go to Mars. You'll do just enough testing on the ground to believe that it'll work. Because, so like I said, back in the 60s, the Nerva, that was tested out in the Nevada desert, and they just exhausted that, hydrogen exhaust gas up into the atmosphere. That's not going to fly, in today's environment. And so the ground test is going to be very sophisticated and very expensive, because you're going to have to capture and scrub out that exhaust gas. So it's going to be precious. And so we won't do near the amount of ground testing that was done for the Nerva program. But we will really think through the testing we need to do, so that then, we'll do, if you will, a lot of our testing on a demonstration flight. Put the engine up in orbit, on a test stage, highly instrumented, and run a burn on it, and probably put it on like a sun intercept trajectory, so that it ultimately flies into the sun. Then we'll look at the data, go back and see what has to change. But ultimately, and by the way, now I'm getting into conjecture because all this is still in work. But yeah, there will be cases where you fire the engine, then let it set for some amount of time, maybe 2 months, maybe 6 months, whatever, and then see if it will refire and operate normally again. Okay. And, we're still, when I say we, I mean the NASA team is still trying to figure all that out. That's all work in progress. But I do suspect that there will be multiple demonstration flights, more so than what we normally do with rocket engines, because the chemical rocket engines can be thoroughly tested and wrung out on the ground. Okay. And we've got great test stands for that. But, that's going to be more constrained on a nuclear thermal engine. So we'll be doing more of our, quote, testing in space.
Gotcha. So is that extra constraining? Are those extra constraints due to the radiation concerns and the fact that you're dealing with nuclear? And also, I've been reading it seems like radiation is less of a concern than I initially thought it was. Could you expand on if radiation is or is not a concern?
Yeah, so radiation, first off, is always a concern. Okay. But the question is, okay, can it be mitigated? What do you deal with it? Okay, so a couple of things. If you're talking about radiation being a concern to the flight crew on a space vehicle, okay, so that's one level of concern. And the answer to that is not much, because your propellant, your engine's going to be back here at the back of the vehicle. Your crew's going to be up here at the front. So you've got that good geographical separation. And, assuming we use hydrogen as the propellant, hydrogen is a great neutron absorber. And it's a pretty good gamma ray absorber. The point is, you get shielding not just from all the geographical separation, but also from the material between you. And in particular, that propellant hydrogen is a very good shielding material. So from the analyses that have been run so far, the crew will see far more health risk from cosmic rays than they do from that nuclear engine back there. Okay, so I just wanted to say that appears not to be much of a concern. Now, when you're talking about handling on the ground, from our experience working with, nuclear reactors for power plants and, in the medical industry, working with high assay, low enriched uranium, people know how to handle uranium. Okay, the procedures are in place with that. So that is pretty well understood. And from fortunately working with NERVA, okay, back in the 60s, we understand, even the basics of firing a nuclear thermal rocket engine. Okay, the thing that I believe will be different is that exhaust stream. Now, the hydrogen, well, as it's passing through the reactor, because it goes through so quickly, is going to be fairly blind to radiation. You're not going to get this toxic exhaust stream coming out. And, but even though it's going to be not terribly hazardous, we don't believe it will be prudent to release it into the atmosphere. Okay, so it'll have to be recaptured. So that'll be the main thing, is dealing with the exhaust stream coming out of the engine. Okay, when you test it like that, everything else about it is not unusual from our existing experience base. And when I say our, I mean the scientific community's experience base of dealing with uranium and the radiation associated with radioactive reactions.
Interesting.
Did that get close to answering your question?
It did. It answered my question perfectly. And it was good to hear that the crew of whatever shuttle would be shielded from radiation. But the exhaust, I was surprised to learn, could potentially be radiated, and you'd actually want to recapture that. So I'm curious then, would you be able to launch the rocket from the ground then, if you have to recapture all of the associated exhaust?
I'm impressed by your question. Okay, so currently the engine is being developed only as an in-space engine.
Gotcha.
Okay, now here's why. Okay, to get something from the ground to orbit requires a lot of thrust. And, we build rockets in stages, and we put a lot of engines or a few big engines like Saturn V, put 1.5 million pound thrust engines on the first stage. Okay. That's because it's having to move a lot of mass, and then it would drop a stage. So you got less, inert mass, and you would keep going. But the point is, you need a lot of thrust to get up. And frankly, you just get better performance from a chemical engine getting up off of the Earth's surface to the atmosphere. Okay,
gotcha.
I can give you a lot of backstory on that, but the bottom line is, you would only use an NTP engine if you had no chemical engines to use. It's just an inferior solution. Okay, but when you're in space, okay, that's where that extra impulse is very, very beneficial. Okay. So the way we explain it to folks often inside of NASA is, getting to orbit, you're thrust driven, but once you're in space, you're impulse driven, if you will. efficiency becomes, wants to dominate once you're in space. But when you're trying to get off the ground, you need all that thrust, all that impulse, because you're moving so much mass. Okay.
Yeah. So weight to thrust ratio, and then I transition to a caring about ISP once you're out of the gravity well.
Yeah. There you go.
Awesome.
Of course, nothing is ever that simple, but I mean, in
Sure.
a nutshell, that's a sort of a good place to start.
Okay.
Sure.
So anyway, I said all that to say, just from a fundamentals of physics standpoint, I don't see NTP being used as a launch, from the surface of the Earth up to orbit engine.
Gotcha.
It's a good clarification. So we've been talking a lot. So basically the solid fuel engines, those are what's kind of the next rocket for space. And and the work you've been doing on the liquid fuel, that's the next generation after that.
Yeah.
I took a quick browse on Wikipedia, and I also noticed they mentioned gas fuel and pulsed nuclear thermal propulsion. Can you quickly expand on those if you have any opinion, or is that not going to be not going to happen at all? Is that not worth talking about?
So, why are we looking at liquid fuel now rather than gas? Because with liquid, at least we've got some ideas about how we could make it work. With gas, we're still scratching our heads. we're like, let's take one really big step first, and once we get the liquid fuel working with what we learn and with the nominal advances in technology, then we'll tackle the gas. Okay. But yeah, right now you show people the gas concepts, and of course, from a physics standpoint, holy cow, it's elegant. It really is. But then when you start talking about, okay, how would we actually realize it? Everybody says, well, let's talk about that tomorrow. Nobody knows.
Okay.
That's good context to have.
I don't know how much you are into science fiction, but our podcast is about bringing sci-fi to reality, right? Is there anything besides the nuclear thermal rockets? Is there any technology or research that you would be interested in hearing more about that we could look into for future episodes?
Yeah, so of course the propulsion stuff is pretty neat. If you there's some great books out there that are also technically very good, like Seven Eves, if you're familiar with that book, or John Sanford did one a few years ago called Saturn Run. Okay, that even as an engineer, I can enjoy the story because it's not so far from engineering viability. Like Arthur C. Clarke, he wrote technically good books too. They weren't just good stories.
Yep.
But yeah, the ones that are most fascinating to me are the ones that are technically credible. And in one of the books, I think it was Saturn Run. I could be off on the book because I do read a lot of science fiction. Interesting, you should ask. But they've developed, they're using the Vasmir engine that has been developed by, I should say is in development by Franklin Chang Diaz. And that engine also has a lot of potential because you can vary the impulse you get in it. And if you will tune your thrust efficiency profile. So, you can lower the efficiency and get more thrust out of it. Okay. And it's a very high performing engine, up in the realm of electric propulsion. And, if you've not talked with him about, the Vasmir engine, you might want to consider that fascinating stuff. And of course, The Martian was just awesome. The next thing, and that's because to really, and I hope I live long enough to see it, but making strides on in situ resources. Okay. Like, for example, being able to effectively utilize the resources. There's a lot of water on the moon. Okay. It's sort of like it's gold there for the harvesting. Can we use that water? Okay. Maybe use it as straight water or split it into hydrogen, that really desirable propellant. Okay. Can we tank up at the moon for these exploration missions instead of having to launch all that massive propellant from the surface of the Earth. Oh, and by the way, water is present throughout the solar system. Can we come up with technologies that let us just tank up as we go? Okay. So yeah, if you want to know a technology that I'm really excited about and will also be a big game changer, it's learning how to tap into the resources that are at the destinations or along the pathway of the destinations that we're wanting to go. That is just really fascinating. And as we move that forward, it's going to change the game.
Well, we'll have to look into that then, and we might have to do a future episode on it. And is there anything that you personally would like to promote via a book or just an idea or some a charity or an idea you really like, etc.?
Well, I tell you what, y'all can do with this what you will, but since you opened the door, I'm going to tell you, okay? One of the hats I wear at UAH is I'm director of the Alabama Space Grant Consortium. If you're familiar at all with the National Space Grant Program, it's okay. Y'all are nodding your head, so you have heard of it. If not, you can go Google it and read about it. And we have a collaborative project underway in Alabama to develop a real scientific spacecraft that is student designed and student constructed. Okay, it's being developed in the senior design curricula at 7 universities across the state, the universities that comprise the Alabama Space Grant Consortia. And we're going to be bidding this 12U CubeSat to NASA's upcoming APRA call. Okay. And by the way, that is a real scientific call, that you have folks like, Johns Hopkins Applied Physics Laboratory and stuff offering proposals to this. This is not a, quote, student competition, unquote. We've been able to line up good NASA mentors, for the student teams. And it's going to be a competitive proposal. That I can tell you. It's being developed. It's called ABEX for Alabama Burst Energetics Explorer. It will be basically a gamma ray burst monitor, but it also includes an X-ray instrument. And, gamma ray burst, it ties into this whole multi-messenger astronomy, dealing with gravitational waves and so forth. And so they've actually, some of the NASA mentors have, pulled in scientific colleagues for a science advisory panel to help, come up with a mission that is doable on a CubeSat. So, like I said, we've got a good scientific mission. We're going to have a good technical proposal. And, what I'm looking to do now is, the big challenge I've got is to raise money to keep this effort going until we get funded by NASA. Okay.
Gotcha.
So, but we're very excited about this. Like I said, it will be, to my knowledge, the first student designed and built, if what I'd call it a full-fledged scientific mission. Okay. On the CubeSat. So, very excited about it. Looking forward to competing and, maybe even winning.
So I wanted to ask you, I mean, you've managed to chase down this career at NASA, and now you're a professor at a university, and you're managing to do all of this really fantastic nuclear thermal propulsion in general. Is there anything that you would attribute your success to, or your success in your specific journey to, at least?
Oh, well, I will say, like I said, it's a combination of planning and serendipity. I always like to, acknowledge that I had some great mentors along the way. And, I tell folks about when I showed up at NASA and I'm full of piss and vinegar and I think I know everything. And there's all these veterans from Apollo that are around. And one of my first technical presentations, they just ripped my heart out. They just cut me up. And then not long after that, I was coming up on one of them in the hallway, and I'm like, oh no, and I'm sort of all meek, and he comes up, stops me, talks to me, says, hey, have you made any progress on this and that? But it was clear that he didn't think poorly of me. This was just part of, helping me grow. Okay. And, that Apollo culture was just fantastic. And I hope I captured a part of that in who I am, which is you don't run away from the hard problems, you run to the hard problems. And you know that there's a solution there to be had, and you just keep digging until you find it. Okay. And I've tried to follow that. That, like I said, that was sort of instilled in me at an early age. And I learned that, being wrong, you learn more than being right. And, that's what those mentors instilled in me is, own your mistakes, and learn. And, don't do the same mistake again. Keep growing, keep learning, and don't be afraid of the hard challenges. Tackle them, learn. Sometimes you will fail, and you know what? It ain't the end of the world. The sun still comes up tomorrow. And the other thing is you cannot plot a career. Like I said, if you had told me 30 years ago or 40 that someday I'd be literally, we call their apparatus the ant farm in the lab, by the way, this Bubbly thermodynamics. Literally, it's 2 sheets of plexiglass, okay, that are spaced, not too far apart. Think of it as sort of like a laptop computer stood up on its edge, 2 sheets of plexiglass, and, we put the liquid in there and we bubble gas up through it, and we film it, and analyze it and see, okay, are we predicting what the bubbles are doing or not? But yeah, if you'd have told me when I was your age that, I would be working on this someday, I would have just said, what are you smoking, dude? So you can't plot this stuff out. A good friend of mine, Larry Sweet, not long after he was installed as NASA's chief information officer, he was being interviewed, and he was asked by the person interviewing him, when you were in college, did you aspire to be, a chief information officer? Did you see yourself? And he said, when I was in college, there was no such thing as a chief information officer. So I guess what I'm trying to say is, be open. That you two guys cannot see very far down the road. So what? Okay, keep learning, keep growing, and keep enjoying. That how I ended up here, I can't explain it, but I've enjoyed the ride.
With that, we will make sure we put all those things that you just mentioned there in our show notes. So anybody that wants to look up any of that stuff, you'll be able to click on a link for it and you'll be able to go check it out, be it in our YouTube video or on whatever podcast platform you're listening to. With that, Dale, thank you so much for being on the show. It was an absolute pleasure to talk to you.
Well, likewise, it's you guys made it very enjoyable to talk to, and I hope you can see that, I warned you in my note, I like talking about this stuff, okay? And so I hope that some of this passion has come across, and I hope you're getting infected by it too, because, trust me, you're going to have gray hair day after tomorrow. It gets here very quickly. And, if you're lucky like me, you'll be doing something that, damn it, I just can't retire. This is too much fun. And that's where you want to be.
I'm glad to hear it. All right, thanks. And that's a wrap. So thank you so much for listening to this episode of Sci-Fi to Reality. We hope you enjoyed it. We also hope that you go check out our website, www.scifitoreality.com. That's www.scifitoreality.com. You can also go check out our Facebook page, Twitter, Instagram, the whole gambit. And you can also find this podcast wherever you personally get your podcasts, along with our YouTube page. I hope that you guys enjoyed it. Give it a share, comment, like, subscribe, all that good stuff for the various recommendation algorithms. We really appreciate it. Thank you so much for listening, and we'll see you in the next one.